Fine. Yes. So good morning, everyone, and thank you, Idris, Kevin, and Elisa for having me here. I'm very happy to be back in Vienna, I think after almost 5 years. I really enjoyed here. And so, yes, I'm also happy to tell you something about, well, the emergence of topological singularities in, let's say, the XY model, and specifically the antiferromagnetic XY model on the triangular lattice. And to start with, I would like to just mention some results on the classical XY model and related models, which also motivate why I want to speak about the emergence of topological singularities. So let's start with the classical XY model. So everything that I'm talking about today will be in 2D. So we are thinking about region omega in 2D, which you can think about as a region, for example, occupied by a magnet. And then on this region omega, we are considering the portion of an epsilon-spaced square lattice. And we have so you can think about the atoms. And then we have an order parameter which to every lattice point assigns a unit vector. So just think about the local magnetization. So, okay, so these are our configurations. And then to these configurations, you associate an energy, which in this simple case is just given by nearest neighbor interactions, and you just sum up the scalar product between nearest neighbors. And then there is a normalization factor epsilon squared, which goes with the volume of a unit cell. And okay, then this whole energy is weighted by a minus alpha, which essentially tells you how ground states of your energy will look like. So of course, the ground states of your energy, they will depend on the sign of alpha. So if the alpha is positive, well then you minimize. Do I have a pointer here? No, wait. Ah, yes, like this. So you minimize each of these terms with the minus alpha in front if all your vectors look in the same direction. So then you make the energy as small as possible. If, on the other hand, yes, and this is typically called a ferromagnet. Think, for example, of iron. Iron is a ferromagnet. If, on the other hand, alpha is less than 0, then you would like to put always antipolar neighbors in for neighboring spins, let's say. And on the square lattice, you can do that. So you can bipartite your lattice. You have 2 sublattices, and you just put antipodal vectors on the 2 sublattices. So it's you can really obtain this global ground state by just minimizing all pairwise interactions. Okay. And of course, so your energy is invariant under global rotations. So I've showed you one instance, let's say, of ground states for each family. But actually, all global rotations of these ground states are again ground states. So it's something which is referred to as S1 symmetry. Okay. And well, this is everything concerning ground states, but actually what the goal is to understand the asymptotic behavior of what is called low energy states, and I will be more precise on that in a minute. But let me just give you an idea of why one is interested in low energy states, because, well, you might be interested in the case where I put some boundary conditions which don't allow my configuration to be a global ground state. So a typical boundary condition would be something where you force your spin field to rotate on the boundary, let's say. Okay. And so low energy states means, well, I'm not allowed to be the global minimizer, so I'm saying my configurations may deviate from my global minimizer. And the way to do that is to say, well, I look at configurations U epsilon such that, well, F epsilon of U epsilon minus the minimum, the global minimum, well, is less or equal than some constant times, well, some vanishing parameter eta epsilon. So this is essentially what is summarized here. So you're allowed to deviate from your ground state. So your energy is allowed to deviate from the minimal energy by a certain amount. And this amount will go to 0 as epsilon goes to 0, so as the lattice spacing goes to 0. Now, okay, you might ask, okay, which scaling eta epsilon is meaningful? This is actually usually part of the problem to understand which eta epsilon is meaningful. And you say that it's meaningful. Well, if with this eta epsilon, choice of eta epsilon, you can get some compactness along your sequence of low energy states. Compactness for certain quantities depending on u epsilon. Might not be the field u epsilon itself, might just be quantities that depend on u epsilon. Okay. Yes. Yes. So everything that I'm telling now is for the ferromagnetic XY model, and for simplicity, I put alpha equal to 1. But the asymptotics on the square lattice for the ferromagnetic and the antiferromagnetic are essentially the same, because you can go with a global change of variable from one to the other. Okay. So now alpha is equal to 1. So maybe let me just do it on the blackboard. What is this f epsilon u epsilon minus the minimum? So, well, if the alpha is equal to 1, maybe I go back to the previous slide, then this is nothing but the sum over all ij, and then I have a minus ui uj, and this will always give me a 1 for every interaction. Okay, and then I probably want to put the epsilon squared. So this is my energy if I remove the ground state. So, and then asymptotics means, understanding the asymptotics of low energy states means I want to characterize the gamma limit of this new energy after removing the ground state energy and rescaling it by eta epsilon, the meaningful quantity. Okay. Now, let me give a name to that. Finally, the XY. So this is what I will refer to as the XY model energy. So the energy after removing the energy of a global minimizer. And well, there is a nice trick that you can do using that your u takes value in S1. You can rewrite this expression over here like in a way of finite differences. So just expand the square here using that u takes the unit value, takes the values in S1, you will end up here. Okay. Well, of course, this is the nice thing about this is that you realize if now I take the piecewise constant, the piecewise affine interpolation of my u, this will give me something which looks like the gradient. If I choose the eta epsilon to be epsilon squared. Then this will essentially look like the gradient of the piecewise affine interpolation. Well, of course, this is nice, but maybe this is a bit too strong. The eta epsilon was chosen a bit too small. And I mean, if you think about the picture that I was drawing in the beginning, so essentially configurations which attain such a boundary conditions, they will not allow you to perform. I mean, you can still do like a transformation like this, but your energy will blow up because you know that, let's say, a function with degree 1 on the boundary of the ball will not be a W12 Sobolev function. So, okay. But there is another energy comparison that you can do. So I did a piecewise affine interpolation. So now my piecewise affine interpolation does not take unit values anymore. So it doesn't take values in S1 anymore. I deviate from S1. But I can control with my energy how much I deviate from S1. So I get another control term here. So this is my deviation from being a unit vector. And I can control it with the energy. And now if you see these two terms here, these are terms that typically pop up in another kind of energy, which is the Ginzburg-Landau energy, which is a typical model for vortices. So you have an energy comparison telling you that I will be more specific on why we choose this rescaling, but forget about the rescaling at the moment. That your energy in the XY model energy on U behaves essentially like the Ginzburg-Landau energy in the piecewise affine interpolation. Well, and the nice thing about that is that the Ginzburg-Landau energy has been studied from the variational viewpoint in several perspectives. So you have properties of minimizers, asymptotics of minimizers, you have lower bounds, and you also have asymptotics via gamma convergence. Okay, and well, the key observation in these results is that if now you have, let's say, a field, now I'm thinking the continuum, you have a field in H1, taking values in R2, such that the Ginzburg-Landau energy can blow up as most logarithmically, then you have a nice compactness property, which tells you that the Jacobian of this field, which in this case is just the L1 function determinant of the gradient, they will converge in a certain sense to measure, which is the sum of Dirac deltas, weighted Dirac deltas. And so flat convergence, it's just it's a weaker convergence as weak star convergence. Let me say like this. And I will tell something more about this later. And yes, so the limiting measures are finite sums of Dirac measures with integer weight. And well, the typical picture that you could have in mind is that in the limit, you have finitely many singularities, and well, your spin field will rotate around these singularities, well, with the clockwise or anti-clockwise, or 1 times or 2 times, and this is essentially captured in the DH. Okay, and then, well, of course, this was for the Ginzburg-Landau, but the same compactness property then also holds true for the XY model energy via the piecewise affine interpolation. Okay, and finally, in this limiting, you have a limiting measure, and using this limiting measure, you can characterize the gamma limit, which will be nothing but the total variation up to a factor pi, the total variation of this measure in omega. Okay, and let me maybe just conclude this section. So typical configurations are really, they look a bit like the X mod X. X mod X shifted and maybe rotated, but they look like X mod X, and this also tells you why, well, why you should expect this logarithmic rescaling, because if you integrate, let's say, the gradient of X mod X on a ball, on a large ball, leaving out a small ball of radius epsilon, which essentially is because, well, we have an epsilon lattice spacing here in this case. So if we want to compare, we should leave out a ball with radius epsilon. Well, but this goes then like the logarithm of the outer radius divided by the inner radius. And this tells you why there is a logarithmic rescaling. And the eta epsilon is in this case, the meaningful eta epsilon is in this case epsilon squared log epsilon. Let me also tell you that, well, this is a very specific case. You can consider, so the X mod X is a very specific case. So you can also consider in general this minimization problem here, where I'm just integrating the gradient of a Sobolev function on an annulus. And I'm requiring that the Sobolev function has degree D on the inner ball. So I'm just saying that, well, my Sobolev function should turn around maybe 2 times here. Then this energy is bounded from below by, again, the same logarithmic contribution, outer radius divided by inner radius, and it's multiplied by the degree squared. Okay. And, well, let me just give you some concluding remarks on this XY model energy. So low energy, as we just saw, low energy configurations in this logarithmic rescaling regime, they develop finitely many limiting singularities. And this is what is typically referred to as topological singularities. And the quantity with which you can keep track of the singularities is the Jacobian of the piecewise affine interpolation. Okay? And, well, we have also seen that the XY model energy behaves like the Ginzburg-Landau in the piecewise affine interpolation. Let me also mention that if you write your spin fields in the angular lifting, meaning that if I write u as the exponential of some I phi, then this XY model energy will behave like the screw dislocation model energy in this angular variable, where where here essentially you have a periodic multi-well potential with a minimal v minimal in the integers, and well, then your phi can be seen as an anti-plane displacement, and well, the fact that here you have you allow for integer shifts tells you that you can have screw dislocations here. So meaning you have an extra line of atoms coming in here. Okay, but maybe this is a bit going beyond what I want to tell you about today, because well, now I've taught you a bit about the ferromagnetic XY model on the square lattice. Actually, I told you the antiferromagnetic XY model on the square lattice behaves the same as the ferromagnetic. And what I want to talk about now is the antiferromagnetic XY model, but not on the square lattice, but on the triangular lattice. And we will see that, well, there the behavior changed quite a bit. But maybe I stop for a moment and ask if there are questions so far. Okay, and then I can go on, maybe. So let me set up the energy. Or, well, the energy we already saw, but the lattice. So we are now considering the triangular lattice, and this is just for comparison. We are considering the configurations living on triangular lattice, still taking values in S1. And we are now considering the antiferromagnetic XY model energy. And for simplicity, again, I just put the alpha equal to be -1 now. So it's just the scalar product of nearest neighbor interactions, the scalar product between nearest neighbors, sorry, summed up and weighted with 1. Okay. Well, we have seen that maybe this is just a picture for nearest neighbors, and we have seen that on the square lattice, I can minimize all pairwise interactions, and I get a global minimum. So I can put antipodal neighbors on 2 sublattices. So this changes if I go to the triangular lattice, and this is typically called what is called frustration. So if I try to do the same thing, I start with a vector in I put the antipodal vector in J. That's of course fine, but then the vector in K really doesn't know what to do. So unhappy, because it cannot be antipodal to both the vectors in I and J. So this is what is called a geometric frustration. So situation where you cannot minimize all pairwise interaction simultaneously due to the structure of the underlying lattice. Well, okay, so maybe you should try to understand what to do instead to obtain a ground state. So it's probably better that you find a compromise between the 3 vectors, I, J, and K. And well, to do that, it's again convenient to rewrite our energy in terms like a square. And again, if you expand the square, you will see that you end up with the same expression here. So where now I just sum up over all the vectors in I, J, K, being the vertices of our right triangle, and I need to remove factor 3. So of course, now this is always positive. And this will be 0 if those 3 vectors, they sum up to 0. So if they rotate by a fixed angle. So in this case, it's 120 degrees. And I'm deciding here, I always rotate counterclockwise. So I, J, K, I always rotate counterclockwise. And well, this is fine. I can decompose my lattice into 3 sublattices, and I always put, let's say, parallel vectors on the sublattice. So on every red sublattice, I have the same parallel vector. On the blue sublattice, I'm rotated by 120 degrees. Again, within the sublattice, I'm parallel, and then the same on the orange sublattice. Okay, but I did one choice here. I decided to rotate counterclockwise. There's actually another family of ground states, which is I just flip the vectors in J and K, which corresponds to I rotate by 120 degrees clockwise. And this is not a global rotation of your other ground state, because I've flipped 2 vectors, so there is a Z symmetry if you want. It's not an S1 symmetry. So this tells you there is another family of ground states. You have 2 families of ground states. And this is not the case if you are on the square lattice. You have 2 families of ground states. And again, this one I can put very nicely competitive so compatible on the 3 sublattices. Okay. So now we have 2 families of ground state, and we also have a quantity which can distinguish between the 2 ground states, which is the chirality. And it's simply, let's say, the cross product between going from I to j, from j to k, and from the k sublattice to the I sublattice. The important thing that you need to keep in mind is it's taking values in -1 and 1, and it's +1 and -1 precisely on the three ground states, on the two ground states. And well, in between, it's just it's somehow keeping track of the orientation. So if my chirality in a triangle is positive, it means that if I go from I to j to k, I rotate counterclockwise. If it's negative, well, I rotate clockwise. But yeah, always going from I to j to k. Okay. And so now we have just found a new quantity. And well, I told you if I'm interested in the asymptotic behavior of low energy states, I want to get compactness results on certain quantities depending on my spin field. So this is a quantity, and we will see that I can actually get a compactness result using the chirality. Okay. So this is now the goal. I want to, again, investigate the asymptotic behavior of this new energy, again, after removing the energy of the energy contribution of a global minimizer. Okay? This is just as a recap. So this is my energy, and this one is now 0 if and only if my chirality on a triangle is equal to +or -1. Okay? So if I want to get compactness or understand asymptotic behavior, maybe it's good to talk about energy barriers. And I have some energy barriers if I consider two neighboring triangles and I want to switch the chirality. So going from a positive chirality to a negative chirality. Remember, I'm always going ijk. This is counterclockwise, and now ijk is clockwise. Okay. Then this energy on the union of the two triangles, I pay at least a constant times epsilon squared in this regime. Okay, but this constant C0 is fixed. Okay, let me just mention for later use that I can also make this argument in some sense continuum. So if I know that in one triangle I'm close to chirality 1 and in the other I'm not, then I also have, I can bound this energy by a constant times epsilon squared. So of course now this constant depends on the threshold that I fixed here. Let's say here I'm larger than 1 minus eta, my chirality is larger than 1 minus eta, and here not, then this constant here will depend on eta. But once you fix the threshold, you find a constant. Okay. So, but let's focus for the moment on this energy barrier here. This tells you that if now I consider a region, let's call it A epsilon, where my chirality is positive, and outside it's negative, well, then I know that along all the all the edges here, I'm paying a fixed contribution. And so this means that I can bound the Hausdorff measure of my boundary essentially by, well, okay, this is just, this doesn't need any energy barriers, but this is just, well, the length of each edge times the number of boundary triangles. But now I know that here, for each of these boundary triangles, I pay a fixed constant for my energy. So I can bound this by my energy. Well, this motivates the scaling that I will now choose. Because this tells you that maybe it's a good idea to choose the eta epsilon as epsilon to make this one finite. And actually, well, this seems a bit like, for people who know, who work a bit on this seems a bit like an Ising system, but in the chirality variable. It's not exactly, because for the Ising system, you are only allowed to take 2 values, but my chirality is allowed to take values in the whole range -1, 1, but I only minimize, so I'm only 0, my energy is only 0 if I'm exactly in the states + and -1. And well, this is somehow summarized in the following results. So if I choose my eta epsilon to be equal to epsilon, I can deviate from the ground state by at most epsilon. Then I know that along these sequences of low energy states, my chirality converges in L1 to a limiting BV function, which only takes values in -1 and 1, so in the 2 ground states. Okay, you could also compare it with mod eta mortula if you want. I also can express my gamma limit in this limiting quantity, so in this limiting BV function or partition. This is let's say, essentially it's a, well, it's an anisotropic parameter if you want. So it's the integral over the jump set of this chirality, and you integrate a certain surface density. And I will not give you the formula for this phi. It's an asymptotic minimization problem, but you can make sense of it. So you have a gamma limit, which it's a bit involved, but you can do that. Okay. So let me say that in this regime, so we see transitions in the chirality, not in the spin field. So the chirality jumps from, let's say, does transition from close to -1 to close to 1, and in the limit you only see -1 and 1. But inside these chirality regions, you can still have a lot of rotations of your spin field. Okay. So now the question is, what happens if I allow my configurations to deviate from the ground state by an amount really less than epsilon? So for example, if I consider the same scaling that we saw for the XY model energy. So instead of epsilon, I'm allowed to deviate from the ground state by an amount of epsilon squared log epsilon, which is less than epsilon. Well, then I rule out the chirality transitions. So I know that my chirality will converge either to 1 or to -1. Because the cost for a transition would blow up. Okay, so now let's assume that my chirality converges to 1. Can we say something about u epsilon, or let's say another quantity related to u epsilon to remove the ficta, but to control, let's say, a bit the rotations that we saw before. So in a similar spirit as for the XY model energy, the classical. So the idea is to compare the antiferromagnetic XY model energy with the ferromagnetic XY model energy. Now, of course, on the triangular lattice, but I showed you the ferromagnetic on the square. For the ferromagnetic, the square and the triangular, the behavior is similar. It's the antiferromagnetic which changes. Okay. Okay. Yes. So this would be the goal, to find a suitable change of variables so that you can compare your antiferromagnetic XY with the ferromagnetic XY on triangular lattice. Okay. Questions so far? Okay, then. Okay, this is from now on my assumption. I'm assuming that I'm allowed to deviate from my ground state by less than epsilon, and my chirality will go to 1. Okay. So then we would like, since we assume that our chirality converges to 1, well, we would like somehow to transform. We would like to do a change of variables based on a suitable transformation of ground states with chirality 1, let's say. So if I think I have a ground state with locally on one triangle, I really have chirality 1, ground state with chirality 1. Then if I rotate on the blue sublattice, so labeled here by J, by 2 pi over 3, or 120 degrees if you want, clockwise, then I transform these two into parallel vectors, which are the ground states for the ferromagnetic. And the same, if I rotate here by 4 pi over 3, then I have a set of 3 parallel vectors, which are ground state for the, again, ground state for the XY ferromagnetic. So if we do that globally, not only for those who have the ground state, those triangles where I have ground states which was chirality 1, then this is a very nice transformation if I'm close, let's say, to chirality 1. But it is a very bad transformation if I'm far away from the ground state of chirality 1. And it's a very, very bad transformation if you are ground state of chirality -1. So indeed, if you have locally a triangle with the ground state chirality -1, and we cannot rule this out on the level epsilon, then I pay 0 for my original energy, but I will pay a fixed constant for my XY model energy, because, well, if you do the same transformation on a ground state with chirality 1, well, essentially you turn it into a ground state with chirality, if I do it on a ground state with chirality -1, essentially I turn it into a ground state with chirality 1, but now I want to estimate the ferromagnetic XY model energy on this one. And well, remember, this one wants to have parallel vectors. So if I'm not having parallel vectors, these are far away from parallel, so I pay a constant. Okay. So this means that I need to estimate if I want to have some hope to proceed, I need to estimate the region where the chirality is, let's say, not close to 1. And well, this is a similar estimate as we saw before for the transition from regions with positive chirality to negative chirality. So remember I told you we can make this argument continuous. So now I'm just assuming that here I have a region with chirality close to 1, and outside I'm not. So I fix the threshold and I say, okay, here I have chirality larger than, let's say, 1 minus eta, and outside I don't have. Then with the same argument as before, I can bound the perimeter of this set. By now a constant which depends on eta, but this one is fixed. Okay. But of course, now I could also use the isoperimetric inequality to bound the area of the set here. And the reason is, since I'm assuming that my chirality converges to 1, I know at least that, well, the region of this area is, so the area of this region is less than the area of the complement. So I can apply an isometric inequality, relative isoperimetric inequality, telling me that then this area is bounded by the perimeter squared, 2 dimension. And well, now this comes with the squared. So I get by the above estimate that this goes like the energy squared divided by epsilon squared. At least this goes to 0, because I'm assuming that my energy is way smaller than epsilon. So it's asymptotically smaller than epsilon. Okay, this goes to 0. But, okay, if now I do a global energy comparison, if I would assume that my amount of energy that I can deviate from, so the amount that I can deviate from my ground state is stronger, is epsilon squared. I'm allowed to deviate from my ground state even less. Then everything is fine. So if my original energy was bounded by this scaling, let's say, scales like this, then I have the same bounds for my ferromagnetic XY, because here I'm getting, I'm also getting epsilon squared. No? But actually, I'm interested. Yes, and also I can compare. This was too much. I can compare the two energies. But actually, I was more interested in the case where here I allow for a deviation from the ground state of order epsilon squared log epsilon. Well, if I do the same here, then you will see that here I'm ending up with an epsilon squared log epsilon squared, which means that globally I can bound my ferromagnetic energy only by epsilon squared log epsilon squared. Which was not the one that I showed you before. This was also an epsilon squared log epsilon. So this seems at first glance like bad news, because indeed, if you had a general spin field for which you only have this worse energy bound with the log epsilon squared here, you would not know that for this you have the nice concentration properties as in the logarithmic, in the pure logarithmic scaling. So instead, you would have that if you rescale the Jacobians, this might still become a diffuse measure. And typically, this tells you that you will see not only an energy concentrated on limiting singularities, but you will see a far field energy. And so in the context of dislocations, you would typically talk about strain gradient models. But again, this is not this is going a bit beyond what I want to tell you. Just telling you, okay, this seems at first glance like bad news, because for a general spin field, I cannot hope to get the same compactness properties. But of course, we don't start with a general spin field. We are starting with a transformation of a specific spin field. And this is somehow the information that we need to use. So the good news is we still have, like outside this bad region, of course, the energy comparison. And we now still know that this the area of this bad region goes to 0, and you need to use it. So you need to keep in mind that you were coming from a specific spin field. So we are coming from a u epsilon. We did the transformation to arrive at the v epsilon here, and then you should remember all the information that you have from the u epsilon. Okay. Maybe at this moment I can tell you the result. So with all these considerations, so we can say if my u epsilon is a sequence of configurations which satisfies the stronger energy bound, and the chirality converges to 1, then well, my now the piecewise affine interpolation of my transformed spin field, this one converges strongly in L2 to a global Sobolev function, so H1 function. But this is in a stronger rescaling regime. And my gamma limit is what you would expect. It's a Dirichlet energy up to a factor square root of 3, which comes from the lattice. Okay. And well, the strategy, well, is I use this nice bound on the area, on the bed area that I have, which tells me that essentially only on finitely many triangles, and finitely meaning finitely not depending on epsilon, I don't have a nice comparison between the antiferromagnetic and the ferromagnetic. And remember, for the ferromagnetic, I can compare via piecewise affine interpolation with the gradient. And okay, for sure you can deal with finitely many triangles. This is not a big problem. Okay, then, but you can use this to show that if now you want to allow for topological singularities in the limit, let's say, if you allow your energy to blow up like epsilon squared log epsilon, you still assume that your chirality converges to 1, then you have a nice discrete vorticity measure. I didn't tell you about this yet, but you can also just think about the Jacobian of your piecewise interpolation of the epsilon. This converges again flat to what we already saw before. So finite sum of Dirac deltas with integer weights and centered in it's finitely many points in your domain omega. Okay, and similar to before, you can really express the gamma limit of your rescaled functions in the terms of this measure me, and will just become up to a factor of the total variation. Okay, let me just wrap up the strategy. So for this vortex scaling, you actually exploit the bulk scaling, and you use a tool which is called, which goes under the name of the ball construction. And well, I think I have a couple of minutes to tell you a bit of the wait. I think I should leave 5 minutes for questions. Okay. Well, okay. Maybe I can mention some ingredients of the proofs. And so the idea is a bit to really work with a discrete vorticity measure, so which you define locally on every triangle in the discrete, and again, which essentially tells you if I'm covering, let's say, S1 by, if I go around the triangle, if I'm covering S1 by rotating clockwise or counterclockwise, or I'm not covering complete S1, and then it's 0. So it's either -1 if I'm covering S1 rotating clockwise, 0 if I don't rotate, and +1 if I'm covering S1 rotating counterclockwise. Okay. And so this is a quantity that I can associate to any triangle, and then just I obtain a measure by just multiplying this with a Dirac delta in the barycenter of the triangle. Okay. So this is a discrete vorticity measure. And just as a remark, the chirality also told you in some way which, if you rotate clockwise or counterclockwise, but the chirality was depending on the sublattice. So it was always distinguishing between upwards and downwards facing triangles. The vorticity does not. And this will become important later. But maybe the more important observation is that I can really find now an S1 valued interpolation where now this is a distributional Jacobian, but I can make sense of a distributional Jacobian of this continuum spin field, which coincides up to a factor pi with my discrete vorticity measure. And well, okay, this goes too far, I think. So I can use this to let's say, essentially estimate my energy again, similar to what we saw in the beginning on annuli, assuming that I have a concentration of measure value. My measure is of the inner ball is equal to d, and my total variation on the annulus is 0. The important observation is that I can bound the total variation on the epsilon level of my discrete vorticity measure in terms of the energy. Because for each, whenever this is non-zero, I pay a fixed constant. Okay, and this is used to get compactness. And well, this is where the ball construction comes into play. So remember, these were the energy bounds that we have. This is a log epsilon, this is a log epsilon squared. So maybe a question that pops up is, why at all do I need the flat convergence? Why can't I, let's assume for a moment that this was bounded by log epsilon. Why can't I, so I told you if locally I have a picture, so if I have a picture like this, so I rotate around S1 one time, let's say this should give me in a global picture like a logarithmic contribution. So now my energy is bounded by this logarithmic contribution. Why can't I conclude from that the total variation of my measure is bounded by a constant, and then I would just have a weak star compactness result? Well, because this is a very local picture, I don't know how my spin field looks close by. Might decide to do something like this. So you start rotating counterclockwise, but then you rotate back and you have a cancellation. And this does not give you the required compactness properties. So this is like what is referred to as a short dipole, and these are the enemies in all your compactness properties. And this is where the ball construction comes into play, because the idea is, well, I should rather combine the singularities on the discrete level, and I should rather consider a large ball containing both or maybe even more of the singularities on discrete level inside, and I average my measure mu. And I define a new measure, let's say mu tilde, which coincides with the average of my original measure on this larger ball. Okay. And this is, well, if you do that properly, this is essentially the ball construction. So you need to do that a couple of times, let your balls expand, and yeah. And so the point in this modification is, if I have this logarithmic energy bound, I can find, let's say, a suitable mesoscale of balls, where I know that if I do my modification that I just described to you before, I get a measure, a new measure, which is bounded in total variation norm, so I have a weak star limit. But at the same time, I know that I'm not deviating too much in the flat norm from my original measure. So this gives you the compactness in the flat for your original measure. But this is if you have this logarithmic bound. If you have the logarithm square, this doesn't work that well anymore. So the concluding remark is, we don't have this this energy bound, but we almost have it, in the sense that, well, all the very bad cases where I have, let's say, ground states close to -1, they will give you a dipole in two neighboring triangles, very short dipole, let's say. So because, well, here I have vorticity +1, here I have vorticity -1. So the log epsilon squared many vortices, they may appear only as very, very short dipoles, and they get eliminated immediately in the ball construction. So, and then it's essentially like, after your first step, you essentially run a ball construction in the usual setting with the usual compactness properties. And then this is sufficient to get the compactness and the gamma limit. And so I think this one I skip. I would just want to summarize that also for the antiferromagnetic XY model on the triangular lattice. You can characterize the asymptotic behavior of low energy states via gamma convergence. And you can have chirality transitions in the surface scaling, which are detected by the chirality. Well, okay. And in the vortex scaling, you have an energy concentration of which you can keep track using discrete Jacobians. And in this scaling, like finitely many point singularities or topological singularities can appear in the gamma limit. And around each limiting singularity, you really store an energy of contribution of order log epsilon. And so, well, a typical picture for the V that you can have in mind, well, this is simplified, is like, again, a rotation of x mod x. Well, then the U looks a bit, if you transform this back, it looks a bit weird at the moment, but if you actually focus maybe just on the red ones, you again see the red vectors, you again see like essentially x mod x. And then you can also see it in the different way that you rotate the ground states around limiting singularities. This is a bit hand waving because you have the compactness in the, again, you have the compactness in the Jacobian and not in the spin field, same. But I think as a typical picture, this is what you can have in mind. And with that, I thank you for your attention.